that dielectric constant. So metal with the dielectric with high dielectric constant are referred to as high K materials. Okay. So for each of these, there are various, they have their specific advantages and disadvantages. Uh, and for semiconductor layer, the bottommost layer, okay, it can be a simple silicon, it can be a silicon germanium material, silicon carbon, or it can be a germanium material, or it can be a gallium arsenide layer. Okay, again, there are various options available for constructing the substrate layer also. So basically, we have to understand that the MOS structure consists of a metal layer, okay, an oxide layer, and the semiconductor layer. And as you know that the metal layer is conducting in nature, okay, or a polysilicon that is used for constructing this top layer is also made to conduct heavily. Okay, the bottom layer is also a conducting layer, okay, semiconductors, and the middle layer is a non-conducting one. Okay, so basically it forms a structure of a parallel plate capacitor, okay, where we have two parallel plates, the upper plate, this one, and the bottom plate, those are conducting in nature. Okay, and these two parallel plates are separated by a non-conducting thin layer. In this case, this is this oxide layer, which is not non-conducting in nature. Okay, so is this MOS structure exhibits its own capacitive effect. Okay, and we call this as a MOS capacitor or MOS capacitive effect. And it is this MOS capacitive effect that plays importantly, that plays heavily in the conductivity of the channel that exists between source and drain. Okay, and we will see how does this capacitive effect affects the conductivity of the channel. Okay, so this is again the three-dimensional view of a simple MOSFET. Okay, look at here. We have seen this several times earlier, but again, just for understanding purpose and refreshing those things. So that this is the metal layer M. This orange colored is the oxide layer. Okay, this is SiO2. Okay, the upper green colored layer is a poly layer here, polysilicon layer that is conducting in nature, and MOS, S is for substrate. No, sorry, S is for semiconductor. Okay, so semiconductor substrate is taken here, and taking it as the base. Okay, MOS structure uh, is formed here. This is M metal, this is O oxide, and this is S semiconductor. Okay, so this is the area where the action will take place. The most important action will take place. Okay, and on the left hand side, there is a source region that is N plus, that is N type in nature and heavily doped. And on the right side of the channel also we have this drain region, which is also N type, and N plus means this is heavily doped with N type impurity. Okay, so basically a channel exists between source and drain. Okay, and the charge carriers will move between source and drain, right? So we have this source terminal that will be coming out, and this is the controlling terminal. We call this as a gate terminal, and this is the another terminal, the third terminal. We call this as the drain terminal. Okay, and we have also the fourth terminal called as the body or the substrate terminal, which is this one. Okay, and for most of the cases the substrate terminal or the body terminal will be ground, will be connected to ground. So in most of the cases, we will see that the source and the substrate are tied together to the ground. Okay, and some sort of voltage is applied on the top of gate and drain. Okay, and drain and source are connected together, so a current flows between drain and source like that, and then from the channel again between source and drain and via the external connected wires and like this. Okay, so the current will always flow between source and drain. Okay, it will not, and because this is because many students do not get this point, so I want to make it clear here. The current will always flow between source and drain. Okay, the current would not flow between gate and source or drain. The current cannot flow from gate. Why? Because the gate is separated by the substrate via a dielectric or insulator. This is basically an insulator layer. Okay, and current cannot flow through an insulator. Okay, so mind it that current would not flow in any case from the gate terminal. Okay, the current cannot flow through the gate terminal. This please take note of this point. Whenever we say that the current is flowing in MOSFET, it is always referred to as the current that is flowing between source and drain. There is no scope of any flow of current, any flow of charge carriers through the gate terminals. No. Okay, but still this is the controlling terminal that controls the flow of current between source and drain. Okay, and how does it control? How does it control? It controls via that MOS effect, MOS capacitive effect. Okay, or that field effect. So when we apply a voltage at the gate terminal, an electrostatic field is developed. Okay, between gate and the semiconductor. Okay, and it is this electrostatic field developed that will control the flow of charge carriers between source and drain. Okay, we will see that effect in detail later on. Okay, and the channel length, basically this is called the channel length. Okay, the length of the gate, and this is called the width of the gate. Okay, width. So generally we know that the length is longer than the width, but here the case is different, as the width is looking longer than the length, and it actually is like this. Okay, so do not get confused. The width will be in most of the cases longer in dimension than that of length of the channel. Okay, so this is the length of the channel and this is the width of the channel. Okay, and then there are several other parameters also, like you can have the dimension of this drain, this particular dimension length, the and this particular dimension, that is the width of the drain. Similarly, we can have the length of the source, this particular dimension, and we can have the width of the source, that is this one. In this case, the width of the source is same as the width of the gate or the width of the channel, that is also same as the width of the drain. Okay, but we are not here concerned about the length and the width of the drain and source. Basically, we are here more concerned about the length and width of the gate or the channel. Okay, that is of more point of focus, point of attention here. Okay, again this is one more figure that shows that particular device, MOSFET. This is showing the four terminals clearly. Look at here, this is the source region. Okay, this is the drain region. Okay, and this is the MOS region, MOS. So this is particularly metal, this is oxide, and this is semiconductor. So this particular is the MOS region here. Okay, and look at this, the drain terminal is not of the same shape as it was shown here. Here we had shown the drain region to be, a perfect rectangle in shape. The source region is also perfect rectangle in shape when we look from the front. Okay, but here this is not rectangular in shape. This one, thin edge is coming out in this fashion here, and similar and symmetric edge is also coming out at the source side. Okay, and this is actually more close to the actual fabricated MOSFET. Okay, in because nowadays you will not find the fabricated MOSFET of this uh, shape, but they are rather of this shape. Okay, and uh, various reasons that why is this edge is coming out in this fashion. Why is this edge coming out? Okay, okay. So this is the MOSFET showing gate body. Okay, remember this, the bulk or the body or the substrate. Okay, so this is the substrate area. This is also known as the body or the bulk. Okay, so we have four terminals in a MOSFET, in a MOSFET device: the gate, the source, the drain, and the body. Okay, this figure I have taken from Wikipedia, so you can go to that particular page and uh, look at it. Okay, so now coming back to the MOS structure and the equations that are describing those, that particular structure. So this is the same MOS structure. Look at this. The top layer is the metal layer. Okay, and this will form the gate terminal here. Okay, so a terminal will be taken out from this top layer, and this will be known as the gate terminal, and a voltage will be applied at this gate terminal. We call this as a gate voltage. Okay, the middle layer is the oxide layer. Generally the most popular one is the silicon dioxide layer. Okay, so that is why it's mentioned here like this, SiO2. So this middle layer is the oxide layer, and the bottom layer is the silicon layer or the semiconductor layer. Okay, this is written here like p-type doped silicon. Okay, now remember that it can be a p-type, it can be an n-type, depending on the device, the type of device that we want to fabricate. Okay, so for n MOSFET it will be p-type. Okay, and for constructing, fabricating p MOSFET, this will be taken as n-type silicon material. Okay, so and remember this is the substrate terminal that's taken out from this substrate or bulk or body area. Okay, and the voltage that is applied at this terminal is generally called as substrate voltage. We can also call this as the body voltage or the bulk voltage, but the more popular term is the substrate voltage, and it is denoted by this VB. Okay, and the gate voltage is denoted by this symbol generally, that is VG. Okay, now in if I talk about the dimension of the various this particular MOS structure, the actual dimensions will be very small, very small. Now, since we know that we are working in nanometer, the researchers are working in nanometer domain. So all these thicknesses, all these lengths and widths will be in terms of nanometers. Okay, there will be some few nanometers, be it this thickness or this thickness or this thickness or this length or this width. All these are basically they can be described in terms of some nanometer dimensions. Okay, So the structure consists of three layers. We know that the metal, the gate electrode, okay, the insulating oxide layer in between, and the p-type bulk semiconductor. Remember, the p-type will be taken for constructing NMOS and MOSFET, and n-type will be taken as for constructing a p-MOSFET. Okay, and the basic properties of semiconductor that we have seen already in, I think, in the subject basic electronics. You might have seen the very famous mass action law that states that in any semiconductor, uh, the product of n with p, that is n dot p, will be equal to ni square. Okay, where n is the concentration of free electrons. Okay, p is the concentration of holes present in that particular semiconductor, and Ni is the concentration of intrinsic carrier. We call this as intrinsic carrier concentration. Okay, so always it will follow that N into P will be equal to Ni square. Okay, and this is equally applicable for intrinsic, or it may be an extrinsic semiconductor. Okay, the law will always hold up, right? Okay. So assuming that the substrate doping concentration is Na, since here we have taken a p-type dope silicon, okay, and for forming a p-type p-type material we require acceptor impurity. Okay, so let us denote that acceptor impurity by N with the substrate capital A. Okay, we can very well, we know this equation that P uh, n naught will be approximately equal to ni square by na. Okay, and p naught will be approximately equal to na. Since we know that when we add our doping material to the intrinsic semiconductor, for example, in this case I want to form a p-type material. So in this case the concentration of holes that we get will be approximately equal to the concentration of doping material that we have added. Okay, and hence we say that uh, the concentration of minority carriers, that is uh, electrons in this case, is almost negligible, because all the doping material that is added in this case to form a p-type material, they will contribute towards the concentration of holes, and not towards the electrons. Okay, so electrons will remain as it is, as it were there when it was an intrinsic semiconductor. Okay, and when we converted this intrinsic into extrinsic, the number of holes increased but the number of electrons remained same. Okay, okay, so look at this, is the energy band diagram of a p-type silicon substrate. Okay, p-type. uh, let's start from the bottom. We know that okay, so energy band diagram represents some energy levels. This is the level that is representing the valence band. Okay, this is actually the top of the valence band. Okay, so it means that this is the top of the valence band, and below this, all this region is the valence band region. So band is something that is a bit, thick. Okay, so this is the top, and below all this region we can take it as the valence band area. Okay, and this is the layer, this is the line for conduction band. So, and this is the actually the bottom of conduction band, bottom of conduction band. So above this area, above this line, All the area that is present above this line can be taken as the area for conduction band. Okay, so it will extend up to free space, right? Because if this is a material, the material is placed in some sort of atmosphere. Okay, atmosphere, and there is a boundary that defines, that is clearly present between the atmosphere and the material. Okay, so there is a defining boundary. So you can imagine that particular boundary here, somewhere here. Okay, so above this, all free space or the atmosphere, and below this, between in this range, is actually the conduction band. Okay, so this is the bottom of the conduction band layer, and this is the top of the valence band line. Okay, and we already know that this particular uh, energy gap is known as the band energy gap or band gap energy. Okay, right? And the value of this band gap energy is around 1.1 electron volt for silicon material, right? And somewhere in between EC and EV, this is the middle point. In between EC and EV, we have an imaginary line. Okay, we have an imaginary line, and we call this as the intrinsic Fermi level. The intrinsic Fermi level for the silicon material. Okay, so this is about silicon band gap, energy band gap. Okay, now when we convert this intrinsic silicon material into a p-type silicon material, we know that when we are adding the acceptor impurity, so because of the addition of those acceptor impurity atoms, one extra layer is formed just above the valence band. Okay, and this particular layer that is formed because of the addition of acceptor atoms in the intrinsic semiconductor, we call this as the Fermi level, or we can also call this as the dopant Fermi level. Okay, dopant Fermi level for this particular material. And this is the case for a p-type silicon material, and you are very well aware that when we form a n-type silicon material, in that case the layer that is formed is nearer to the conduction band. Okay, for n-type material, but for p-type material, this particular extra layer that is formed is nearer to the valence band. Okay, so there is still some gap between this Fermi level that is formed because of the addition of the impurity atoms and the intrinsic Fermi level that is present at the middle of EC and EV. Okay, now uh, there are some terms that you might be aware of. There is one term called as electron affinity. Okay, electron affinity. It is denoted by this symbol Q into xi. Okay, so we can define this term electron affinity as the energy required by the uh, electrons to escape from the metal. In a very simple words, we can define like this. Okay, and being specific, we can define as the electron affinity as the energy difference between the free space and the conduction band. Okay, the energy difference between the free space and conduction band is called as the energy affinity. Okay, and obviously there is an energy gap between the newly formed Fermi level and the intrinsic Fermi level. Okay. So the question will come in mind that how is this electron affinity how is this electron affinity is different from work function, right? So if you can remember the definition of work function, this time is already 3:20. Okay, so coming very quickly, going very quickly. We can define the work function as the minimum thermodynamic energy needed to remove an electron from a solid to a point in vacuum immediately outside the solid surface. Okay, so this is the definition of work function. That is the energy required to remove an electron from a solid to a point in vacuum immediately outside the solid surface. Okay, and here, as I have said, that electron affinity is the energy required to extract an electron from the conduction band into free space. So these two terms are, sounding similar in definition. They are sounding similar in meaning also. Okay, so we will try to clarify this in the next class, and then we will proceed further. Okay. Tomorrow is our class. I think from 12:20 or I think from 12:20. So, anything from today's class, students? Any points? Any doubts? You can ask your doubt, or in the chat box, you can ask via audio, via your headphone, and also you can post. You can give your attendance in the chat box. Just write your roll number and name in the chat box, and then you can leave. अभी हो गया है बख्तियारपुर तो वही है ना बख्तियारपुर तो मेरा ससुराल है वहीं से नीतीश कुमार वहीं पे उसका आसपास घर भी है उसका सिमरी तुम हो गया एरिया वहाँ पे आसपास एरिया